All right, welcome everyone. Today, we're going to pull back the curtain on machine learning. We're going to break down the big, core ideas piece by piece so you can really see what's going on under the hood. Let's get right into it.
So this is the big one, right? We hear the term machine learning all the time, but what does it actually mean for a machine to learn? I promise you, it's not magic, it's a process, and it's built on some really solid and pretty fascinating foundations.
And that's exactly how we're going to tackle this. Think of it as a journey. We're going to explore the foundational pillars one by one, building our understanding from the ground up. By the end, you'll have a really solid framework for how this whole thing works.
Our first stop, and you could argue it's the most important one, is the fuel that powers the entire engine, training data. Honestly, without it, nothing else we're about to talk about is even possible.
But why all the fuss about data? What is the big deal that makes it so absolutely critical? Well, the answer is actually pretty intuitive when you think about it.
I love this analogy. Think of an ML model as a brilliant chef. You can give that chef the most high-tech, fanciest kitchen in the world, but if you don't give them any ingredients, they can't cook. Data is the ingredients. It provides the raw material, the examples, the patterns, everything the model needs to start learning.
And this isn't just some gut feeling people in the field have. It's actually a formal concept in computer science called pack learning. And the main takeaway is super simple. The more complex your model is, or the more accurate you need it to be, the more data you're going to have to feed it. It's a direct trade-off.
Okay, now don't let this formula scare you. We are not going to do a math quiz here. The only reason I'm showing you this is so you can see that there's a real, direct, mathematical link between a model's complexity, its accuracy, and how much data it needs. This is the formal proof behind that simple saying, more data is better.
All right, so we've got the fuel. Now let's pop the hood and look at the engine itself. How does a machine take all that data and actually use it to form ideas? How does it get from a bunch of raw numbers to something that looks like a prediction?
Let's make this real. You and I, we know what a cat is. We see a picture of one, we instantly recognize it. But a computer doesn't see a cat like we do. So how in the world does it capture the idea, the very concept of a cat?
Well, it does it by breaking the concept down into a collection of measurable features. So instead of one whole picture, it sees a set of numbers that represent things like fur texture, the angle of the ears, or the presence of whiskers. A cat isn't a picture, it's just a specific point, a cluster of numbers in a giant mathematical space. And once concepts are just numbers, making a prediction becomes a math problem. The core idea here has a fancy name, function approximation. We just assume that somewhere out there, there's a perfect, true mathematical function for identifying a cat, and the model's entire job is to build its own function that gets as close to that perfect one as it possibly can.
This is a great way to think about it. Imagine there's a perfectly smooth curve drawn on a piece of paper. Now try to trace over it with a pen. Your line's going to be a little shaky, right? It won't be perfect, but with enough care, you can get incredibly close. That is exactly what a machine learning model is doing. It's trying to trace that true answer using the data it has.
So that's kind of how a model thinks. But you have to remember, these incredible ideas didn't just pop out of nowhere. They are the result of a really fascinating journey, one that spans decades of research full of amazing breakthroughs and some really frustrating dead ends.
I mean, just look at this timeline. The first seeds were planted way back in the 50s. But then, for decades, it was kind of slow progress. And then, bam! Look at what happens in the 2010s. The field just explodes. What on earth changed?
Yeah, this is a really important part of the story. Before that big explosion, there was a deep freeze. People in the field call them the AI winters. For long stretches, especially in the 70s and 80s, progress just stalled and a lot of the funding dried up. The excitement was there, but the results just weren't. So, what was missing? And the answer, believe it or not, brings us right back to our very first pillar. The math was often ready to go. The core idea for a lot of modern AI was actually figured out in the 70s. But the resources weren't there. Computers were painfully slow, and crucially, there just wasn't enough data. The theory was basically waiting for the rest of the world to catch up. Okay, so now we have the theory and we've got the history. Let's get practical. How does someone actually build a machine learning model from start to finish? It's not just about writing a bunch of code, it's a really structured, systematic process. And that process usually follows these 4 key phases. First, you have to figure out what problem you're trying to solve. That's scoping.
Then comes the really heavy lifting, data prep. Only after all that do you get to the fun part, the modeling itself. And you're still not done. Finally, and this is so important, you have to actually deploy it and then monitor it to make sure it's working out in the real world.
And that leads us perfectly into our final pillar. We've built a model, it's out there running, but is it any good? How do we measure success? Because a model is totally useless if we can't tell whether it's actually getting things right.
First things first, you have to know what kind of game you're playing. Are you trying to predict a specific number, like the price of a house? That's a regression problem. Or are you trying to sort things into categories, like spam or not spam? That's a classification problem. And you measure success for each one very differently.
For classification, this little table here is your absolute best friend. It's called a confusion matrix, and it's key because it shows you not just if your model was wrong, but how it was wrong. For instance, if it correctly flags a spam email, that's a true positive. Great. But what if it accidentally marks an important email from your boss as spam? That's a false positive. It gives you a much richer story than just a single accuracy score.
And from that matrix, we get two supercritical metrics. The first one is called precision. A good way to think about precision is to ask this question. Of all the emails I pointed at and yelled spam, how many of them were actually spam? It measures how reliable your positive predictions are. And then there's recall, which just flips the question around. Recall asks, of all the spam emails that actually existed out there, how many did my model manage to catch? This measures how complete your model is, how much it lets slip through. You can see there's a trade-off, right? A model can be really precise, but miss a lot of spam, or it can catch all the spam but maybe make a few more mistakes. Knowing the difference is key.
And there you have it, the foundational pillars of machine learning. The absolute necessity of data, the clever way machines represent concepts, the long history that got us to this point, and finally, the crucial metrics we use to see if it all works. We've laid the groundwork. So the real question is, now that we understand the foundation, what incredible things are we going to build on top of it?